Hello everyone, in this video we will be discussing dot points 12.6 and 12.7 which relate to the calculation of pH. I just want to quickly start by recapping the pH scale. So I'm sure you've seen this before. pH scale goes from 0 to 14 with 7 being neutral, and a lower pH than 7 is acidic, a higher pH than 7 is basic or alkali. The lower the pH, the more acidic a solution is. So a pH of 0 is more acidic than pH of 1. And on the other side, the higher the pH, the more basic a solution is. We're going to look at exactly what pH is and how you can calculate pH given any concentration of hydrogen ions. So you can use this as your first subheadings for pH. pH, the word pH itself stands for power of hydrogen, and it is a number that reflects the molar concentration of hydrogen ions, or H+, in a solution. So a number that reflects the molar concentration of hydrogen ions in a solution. This is the formula for calculating pH. It's negative log to the base 10 of molar concentration of H+, and you will see here that I have used a square bracket to represent that. So a square bracket explicitly implies molar concentration of something. So if I write square brackets H+, it means concentration of H+ in mole per liter. So other example, for example, if I want to write molar concentration or concentration in mole per liter of, say, HCl, then that's the same as square bracket HCl. So whenever you use square brackets in chemistry, it represents not just concentration, but specifically molar concentration or concentration in mole per liter. So I just want to really quickly talk about the log scale, or what log to the base 10 actually means. Now, first of all, you don't have to do anything without a calculator. So if you have a calculator, you're going to look at this button, which is the log. So there are two log scales that are in your scientific calculator. The one that write log, so log is the same as log to the base 10. And what it is an operation that allows you to find the power of something. So for example, if I input log to the base 10 of 1,000, now 1,000 is the same as 10 to the power of 3. So this is equivalent to log to the base 10 of 10 to the power of 3. Then if you put this expression in your calculator, that is going to come out 3. So the logarithm of operation allows you to find the power or the exponential of a number, so that given this being the base. So if I have log to the base 10 of 10 to the power of negative 2, then it's just going to equal to negative 2. So it's just going to give whatever that power is, as long as the two bases are the same. If you want to find log to the base 10 of numbers that are not an exponential of 10, say for example, I want to find log to the base 10 of 1.6, this is not something that you can do without a calculator. And I mean, I don't expect you to do any of this without a calculator anyway. But all you need to do is just go into the calculator and type log of 1.6. And so in calculator, or on calculator, just go log 1.6. And it should come out as 0.204, and that is going to be the answer. So all you need to do is to use this button, log, in your calculator, and then you should be okay. All right, I'm going to go through a few examples of how you can calculate the pH of different solutions. So just remember the formula for pH, as we discussed earlier, is negative log to the base 10 of the molar concentration of hydrogen ion. And you can also just write it as negative log of molar concentration of hydrogen ion, because the log in your calculator will be log to the base 10. Okay, so the square brackets mean molar concentration, or concentration in mole per liter. Okay, so if we look at these three examples, calculate the pH of the following acidic solutions, assuming complete ionization. So let's just start with the first solution. So the volume is given to be 100 ml, and the molar concentration of hydrochloric acid is given. So the molar concentration of HCl, I'm going to use the square brackets here, is 0.15 molar. So this is the molar concentration. And you need to find the pH, and this is the formula with the pH. So in order to do that, you need to convert from the concentration of the acid to the concentration of hydrogen ions. This is where the word complete ionization comes in. Complete ionization or fully ionized is the phrase that we have seen before to define a strong acid. Just means that all of the hydrogen ions in the acid will be ionized into water. So OH plus in the acid go to water. Now, what this means in this particular case is that if hydrochloric acid has only one hydrogen ion, and we assume that all of the hydrogen ions will go to water, then the concentration of hydrogen ions would equal to the concentration of hydrochloric acid, which is 0.15. Okay, so the concentration of hydrogen ions will be the same as concentration of hydrochloric acid. So if I already have the concentration of hydrogen ions, I can find pH just by following the formula. So negative log of 0.15, and you put this in the calculator, so you have negative log of 0.15, and I get a pH of 0.82. Let's just do 2 decimal places. So you can see this is a fairly acidic solution, it's very low pH. Let's do the next question. 100 ml, so the volume is the same. Now, I'm sure you can see by now, but the volume actually is not required to calculate pH. You just need the concentration. And now we have a different concentration and a different acid. So the acid is sulfuric acid, and the concentration is 0.2. We're still assuming complete ionization, but not only does this acid have a different concentration compared to the previous example, this is also a diprotic acid, whereas the previous example was a monoprotic acid. A diprotic acid means that the acid has 2 hydrogen ions available for donation. So the amount of hydrogen ions that can go into water is going to be 2 times the concentration of the acid. So if the concentration of acid is 0.2, the concentration of hydrogen ion will be 2 times 0.2, which is 0.4 molar. And this is because the acid is diprotic. Okay? So you have to really pay attention to the formula of the acid. If there are 2 acidic hydrogen ions that are available for donation, then you need to factor that in when you find the concentration of hydrogen ion. So now that I have that, I can find the pH using the same formula, just negative log of 0.4. And you should get 0.3979 or something like that. So 0.340, it will go, what am I doing? 0.40 if you're going for decimal places. Okay, so that's example 2. All right, let's look at number 3. I'm gonna I'll write the volume. So the volume is still 100 ml, and you have a different acid now. The acid is nitric acid, and the concentration of nitric acid. Now, because this concentration is not in mole per liter, I can't use the square brackets for it. So concentration of HNO3 is 1.31% mass per volume. So I have an extra problem here. This is a monoprotic acid, so it's good, but I don't have the concentration of this acid in mole per liter. So you can't calculate pH unless the concentration is in mole per liter. So what I need to do for this particular case is I have to convert this concentration to mole per liter. So 1.31% mass per volume is 1.31 grams in 100 ml. So it's a percentage mass per volume. And this is the concentration of nitric acid. So I just need to convert the mass of nitric acid to the number of mole via molar mass. So the molar mass of nitric acid, if we find this quickly, it would be 63 grams per liter. Sorry, gram per mole. So if I have 1.31 grams in 100 ml, I just need to divide that mass by the molar mass to get to number of mole. So that would be 0.079 mole in 100 ml. And then you need to convert it to mole per liter. So 100 ml is the same as 0.1 liter. So I just tidy it up. It will be the same as 0.2079 mole per liter, which is molar concentration. So this is the concentration, the molar concentration of nitric acid. Because this is a monoprotic acid, this is the same as the molar concentration of hydrogen ion. And then from here, let's see whether we can squeeze in the final answer. We can find the pH, which is just negative log of 0.2079, and then you do that in the calculator. And you get 0.668. So this is a pretty acidic solution as well. Okay, so those are the three examples. So from these three examples, the first few points that I want to emphasize regarding pH or interpreting pH values, the first one is that when you calculate pH, or in the calculation of pH, I don't even know what I'm writing here. So to calculate pH is what you really should write here. To calculate pH, the concentration of hydrogen ions. So it has to be hydrogen ions and not anything else. And the concentration has to be in mole per liter, must be used. So to calculate pH, the concentration of hydrogen ions in mole per liter must be used. So we can't use the concentration of the acid. You have to convert that to concentration of hydrogen ions, and you cannot use a concentration that is not in mole per liter. So you have to do any conversion necessary if the question hasn't given you concentration of hydrogen ions in mole per liter. The other thing that I do want to emphasize is that when you have a strong acid, because the definition of a strong acid is that it fully ionizes in water, so you can assume complete ionization. So you can, for example, if I have HCl, I know that all of the hydrogen in HCl is gonna get ionized. So you can just make that assumption and find the concentration of hydrogen ions from the concentration of the acid. The issue is when you have a weak acid, and I haven't actually given you any weak acid in the three examples just before, but a weak acid only partially ionizes in water. So in a weak acid, it is often not possible to determine the concentration of hydrogen ions from the concentration of the acid. So a weak acid that we have looked at before is ethanoic acid, which is vinegar. And remember that because it partially ionizes, it can be written like this. So the way that you can understand this is if I have a concentration of 100, well, let's do 10 mole per liter. If I have 10 molecules of the acid, because it is complete ionization, I know that all of that acid is going to end up as hydrogen ions. So if I know what the concentration of the strong acid is, I can work out the concentration of hydrogen ions, just a direct complete ionization. However, because vinegar is a weak acid, if I start with 10, I know that not all of them is going to form hydrogen ions. So you know that it's less than 10, but you don't know exactly what percentage of ethanoic acid it's going to get ionized. Like, is that half? Like, is it 7? Is it 3? So it's actually not possible to know. So because of that, you can't calculate the pH of a weak acid in this way. So I know that the molar concentration is going to be less than 10 because this acid only partially ionizes, but I cannot know exactly what that concentration is. So what I'm trying to say is that I'm not going to ask you to calculate the exact pH of a weak acid, at least for this year anyway. There are other ways to do it next year that we may look at. And the reason why you can't directly calculate it is because you cannot assume complete ionization when the acid is weak. So that's a few points between strong and weak acid, which I strongly recommend that you have this in your notes. All right. I have discussed this, so I don't know why I have it here. Let's just talk about the other two examples, which are D and E. And this is another point that I want to make. So I'm going to do this again, concentration for part D. So the volume is still 100 ml. Have I done this before? No, it's a different, okay, it's a different concentration. So the concentration, molar concentration of the acid is given, again, which is good. It's already in mole per liter. You're still assuming complete ionization, and this is a monoprotic acid. So the concentration of hydrogen ion is the same as the concentration of the acid, which is 0.20 molar. So the pH is negative log of 0.2. So we're just going to go negative log of 0.2. And this is 0.698. Okay, let's do 0.70 if you round it up. Now for the next example, 100 ml again, the concentration of the acid is 0.30. Once again, it's monoprotic. So the concentration of the acid is the same as the concentration of hydrogen ions, and it is 0.30 molar. So pH is negative log of 0.3, negative log of 0.3, and it is 0.52. So I think the point that I'm trying to make here is that you can have the same acid, but two different solutions of the same acid can have two different pH values as long as the concentrations of the acid has changed. So just because an acid is like hydrochloric doesn't mean that you always need to have the same pH. Okay, it's just a reflection of concentration, and concentration can change if you add more water or if you make it more concentrated. So the pH will vary depending on the concentration, even from the same acidic solution. But the other thing that's probably noteworthy is that if the solution has a higher concentration of acid or higher concentration of hydrogen ions, then the pH will become lower, as you can see here. I think that's probably something that you know already. But the lower the pH, the higher the concentration of hydrogen ions, and the more acidic the solution. So if you have a pH scale, and let's say 7 is neutral, so if you're going this way, and let's say that's 0, then it's going to become more acidic as the solution gets closer to 0. So you have like two different solutions here, and even if you don't know the exact pH, you should be able to work out which one is going to have the highest and the lowest pH. So in terms of hydrogen ion concentration, solution D has the lowest hydrogen ion concentration. So solution D is going to have the highest pH, followed by solution C, followed by solution A, 0.1, and followed by solution B. So in terms of pH, you're going to have B having a smaller pH than A, having a smaller pH than C, having a smaller pH than D. And that is because the concentration of ions, B has the highest concentration, and then A, and then C, and then D. So there can be questions when you have to predict the pH values of two different solutions just by comparing their concentration of hydrogen ions. And similarly, the same acid, I've mentioned this before, the same acid at different concentrations would have different pH values. So these are the other 2 points relating to pH that I want you to know. It's probably a good idea to also go back and discuss these 3 concepts and how they are different from each other. The first one is strength of an acid. Now, strength of an acid is whenever you have like a strong acid or a weak acid. So a strong acid fully ionizes and a weak acid partially ionizes. And then the second concept is concentration of acid, and this represents the ratio between the amount of acid and the amount of solution. So, for example, concentration of acid could be HCl is 0.1 molar, or H2SO4 is 0.1 molar, something like that. Whereas strong versus weak acid is when you're looking at whether it fully ionizes or partially ionizes. So this is strong versus weak, CH3COO minus and H plus. And the last concentration is pH values, and this represents the concentration, the last concept is pH value. It represents the concentration of H plus ions in the acid solution. So the thing that I want to emphasize here is that these 3 concepts are not the same thing. Strength of an acid does not reflect the concentration of the acid. And the concentration of the acid is not a direct representation of pH values. So these 2 solutions have the same concentration of the acid, but the hydrogen ion concentration is going to be different because one acid is monoprotic and one acid is diprotic. So even though these 2 acids have the same concentration, their pH values will actually be different. Okay. I also want to use this to remember that diagram that we talked about last lesson about concentrated versus diluted solutions and strong versus weak acids. So we can put that in a pH scale. So this solution, I think this was the question in the homework actually. So there are 4 solutions, and you can actually order them from the most acidic to the least acidic. And the most acidic solution is going to be this one, simply because you have the highest concentration of hydrogen ion present. So you see, you can have 6 hydrogen ion molecules. So we can assume that the concentration, for example, is 6 mole per liter. The second most acidic solution in this case is going to be ethanoic at 3 mole per liter, being the concentration of hydrogen ion. Now that's extremely acidic, I have to say. And then the next one is at 2. So you have 2 hydrogen ions in this solution. And then the last one, which is the least acidic, is going to be the first one, or this one, which with only 1 hydrogen ion in the solution. So you can see that a solution of a weak acid, which is in this case ethanoic, a solution of a weak acid could have a lower pH than a solution of a strong acid. It really depends on the concentration. So if you have a very, very diluted strong acid solution, the pH of that solution may even be higher than a concentrated weak acid solution. Anyway, so don't take pH as a direct representation of how strong the acid is. It just tells you how many hydrogen ions is there. You can have a strong acid and a weak acid solutions with the exact same pH as well. All right, now this is a good time to do question 1 and 2. And then, yeah, you can pause the video or to complete this question, or you can just keep watching. We're just going to talk about another thing, and then we finish for today, I think. So the other thing is, if a pH is given, the molar concentration of hydrogen ion can be calculated to be as follows. So concentration of hydrogen ion is 10 to the power of negative pH. So this is just the reverse of a logarithm. I'm not going to go into the details of what a logarithm is. I'm just going to say that if you have a calculator and you know what the pH is, 10 to the power of negative pH can give you the concentration of hydrogen ions. So for example, I'll give you the examples here. The pH of a solution is 2.5, shouldn't have a molar here. Calculate the molar concentration of HCl. So pH is 2.5. Now, if we just recall the formula, the concentration of hydrogen ion in a solution is 10 to the power of negative pH. So if the pH is given, if I just take 10 to the power of negative that, I can find the hydrogen ion concentration. I think that's supposed to say H2SO4. Okay. So if pH is 2.5, the concentration of hydrogen ion is going to be 10 to the power of negative 2.5. And you probably want to put this in the calculator. So 10 to the power of negative 2.5, which I would get 0.0032. So molar concentration, okay? And because HCl is monoprotic, there is only one hydrogen for every HCl. I know that the concentration of HCl would equal the concentration of hydrogen ion, and it would be 0.0032 molar. So this is the final answer. Let's do one more example. The pH of a H2SO4 solution is 2.5, so pH is 2.5. And I need to find the concentration of the acid again. So I'm just going to start by finding the concentration of hydrogen ions from the pH. So it's the exact same operation as before, and it should give you the same concentration as before. So the concentration of hydrogen ions is 0.0032. However, the difference between this and the previous example is that this one is a diprotic acid. So with a diprotic acid, for every acid, you have 2 hydrogen ions available for donation. So the amount of H2SO4 is going to be halved the amount of hydrogen ions. So in order to find the concentration of H2SO4, I need to divide this by 2. So you will get 0.0016 mole per liter. So that's how you can determine concentrations of the acid using pH. Okay, I only have one example left, and then there are a couple more questions that you can do. And this has to do with dilution and sampling. So let's just go through example G. 15 ml of an HCl solution. So volume is 15 ml. And this solution has a pH of 2. So you have 15 ml of an acid, hydrochloric, has a pH of 2. And the question asks how much water should be added to dilute the solution to increase its pH to 3.5. So this is essentially the original solution. And you have to dilute. Remember, with dilution is C1V1 equal to C2V2, such that the new, you don't know what the new volume is, but the new pH has to be 3.5. So remember that with an acid, the lower the pH, the more acidic it is. So if you want to decrease the acidity of an acid, you can do that by adding water. So when you add water, the pH of an acid will increase as it becomes less acidic. Now, in order to do this question, you're still going to have to use the dilution formula. The catch here is just that you have to do one extra step, which is to convert from pH to hydrogen ions concentration. So because pH is 2, I know that the concentration of hydrogen ion in the original solution must be 10 to the power of negative 2, which is 0.02 molar. So this is going to be your C1, the original concentration of hydrogen ion. And I need to dilute the solution such that the new pH is 3.5. So the new hydrogen ion concentration will be 10 to the power of negative 3.5. Now, I don't expect you to do this by hand. So you can put this in in your scientific calculator, and you will get 0.000316. So the new concentration is 0.000316. Okay, so now that I have C1 and C2, I can work out the new volume. So the new volume is just C1V1 over C2. So 0.01 times 15 over 0.000316. So you can find V2. And I got 474 milliliters. which implies that you're going to need to add the difference between these two. So 474 minus 15 is 459 ml. So this is the volume of water that needs to be added. Okay, so that's that for today, and try to do the last 4 questions of the worksheet. And thank you.